All right, our second video here from chapter 10 is a little bit on the longer end. We first talk about elimination reactions of alcohols, which is also known as a dehydration because you end up losing water. And then we talk about oxidation of alcohols. And at the end of this video, we'll be done with the alcohols part of chapter 10. But like I said, it is a little bit of a longer video. So feel free to break it up into two smaller parts. Maybe do elimination reactions first and then do the oxidations after if you're pressed for time. If I hadn't already committed to making 4 videos for the chapter, I might have even split this one up into 2. Okay? But dehydration / elimination first and then oxidation after. Okay? To conclude alcohols. So elimination reactions of alcohols, right? We've got tertiary to consider and then primary and secondary. It's called a dehydration because, as I mentioned, it's a loss of water, right, via an elimination reaction. Just like when you're dehydrated, you don't have water, right? When these things lose water, it's called a dehydration reaction, and it's occurring via an elimination mechanism. Right? Here's what it looks like. We lose an OH and an H down here. Okay, so HOH or H2O, right? You lose water, and you formed an alkene, like you know from an elimination reaction from chapter 9. Okay, so dehydrations are eliminations, but what's a little bit different here? This is an acid catalyzed reaction. Okay? Here we require both an acid catalyst and heat, right? Remember that delta symbol represents heat. Usually sulfuric acid is used as a catalyst for this reaction. It's done to promote your leaving group. Okay? So let's look at what that mechanism looks like. Okay? Well, we have our sulfuric acid, as I just mentioned, right? Our acid protonates our leaving group. And that happens, no problem in solution, because that oxygen is the most basic atom in solution. Okay, so that takes our OH to an H2O. It's a better leaving group. Okay, that leaves, which gives us a carbocation. That's step 2. Okay, notice here, right? This is going via an E1 reaction. We have that carbocation intermediate. Okay, and then our base comes in, pulls a proton off of the beta carbon, and forms your alkene. Okay. In this case, water is acting as a base because it's in higher concentration. You could also show this acting as a base. Either one would be fine for the purposes of my course. And right here, right, this beta hydrogen is the same as this beta hydrogen. Thinking about it in 3D, it forms the same product over here, and that's cyclohexene. Okay. But if it's not symmetrical, right, you can end up with having a regioselective reaction. Here we've got 2 acid catalyzed dehydration reactions. And just as we would predict from chapter 9, the more substituted alkene is the major product. Okay? So looking at this alkene down here, we've got 1, 2, 3 alkyl groups surrounding the alkene versus over here where we only have 2. Okay? Over here, 1, 2, 3 alkyl groups versus again, just 1, 2. So the more substituted the alkene, the more stable it is, the major product you're going to form, right? If you have a choice of where to make this. Okay. And again, why do these predominate? We know that from chapter 9 already, okay? Because it's the same first step in an E1 reaction. Okay? But then for the second step, the transition state for the more stable alkene is formed faster, and thus it's the major product in solution. Okay. And one thing you might notice is the conditions for this reaction, right, are the polar opposite of what we saw in chapter, I think 6, this reaction was first introduced, right? The first thing you learned how to do, right, one of the first reactions you learned was take an alkene plus water and an acid catalyst to get the acid catalyzed addition of an alcohol, also known as a hydration here, going from right to left. Okay. Now we're doing the opposite, right? Still adding an acid catalyst with heat now and doing a dehydration reaction to form an alkene. So how do we control that equilibrium, right? How do I actually get this reaction to go from left to right if that's what I want to do? Right? Well, I can't just leave everything sitting around or we'll revert back. So typically, right, you take your alcohol, you dehydrate it, you form an alkene, and then you remove that alkene by something like distilling it. Okay, it's got a lower boiling point than the alcohol, so you can remove it by distillation, right? And then removing the product will drive this reaction from left to right You know that from Le Chatelier's principle. Okay? The slow step here is the formation of the carbocation. So that is going to control the overall rate of the reaction, right? Formation of the carbocation is the rate determining step. The easier it is to form the carbocation, the faster the reaction. So your tertiary alcohols are going to react the fastest. Okay? Tertiary are going to react the fastest, followed by secondary, followed by primary. Okay? These tertiary alcohols are the easiest to dehydrate, but again, just have that mental check. Make sure you're considering any possibility via an E1 mechanism of a carbocation rearrangement, okay, which is shown here on this slide, right? Dehydration reaction, do I have a tertiary alcohol? Okay. Well, in this case, it's actually a secondary alcohol. They do E1s as well. Right. So I've got my secondary carbocation. Can it move? Well, it's not going to go to the right because that would be primary. But over here, right, that would be more stable. I don't have a hydride shift that can occur because it's all methyl groups, but I can methyl shift over, gives me a tertiary carbocation, right? It's upgraded from secondary to tertiary. And then I form the more substituted alkene as my major product. Yep. And there should also be an H3O plus as a product as well over here. Yep. Now, what about primary alcohols? Yep. We're not going to form a primary carbocation. Right? So those are going to go by an E2 reaction. Okay? So tertiary and secondary alcohols, those are going by E1 eliminations, okay? Dehydrations. Now, if it's primary, okay, same first step, protonating the leaving group, okay, but then you're in E2, so everything's happening at the same time. Base pulls off the beta carbon, electron density shifts over to form the pi bond, your leaving group departs, all at the same time. Okay? You see right there, it's an E2 reaction. You should be familiar with those mechanisms now from chapter 9. Okay? But we actually have a competing reaction as well, right? With that protonated leaving group, this notice right here is the same as what we've got right here. We also have competition from our alcohol acting as a nucleophile, okay? Coming in, attacking that, kicking off the leaving group, okay, forming an ether, not too different from the Williamson ether synthesis. Yep. So that would be a substitution product. We've got two competing reactions going on, okay? And that's why heat is key. Remember, a higher temperature favors elimination reactions. Okay, so it's not actually shown here, but you'd want to include that delta, right? Higher temperature is going to favor your elimination product. Okay? But you're always going to have some degree of competition. So it's not a great tool for synthesis. Okay, so again, primary carbocations, primary alcohols, if you're dehydrating them, it's going via E2, secondary and tertiary will be E1. Okay. What about some longer alcohols? If I have a longer alcohol here, it's a primary alcohol, 1-butanol, right? I've got my conditions for elimination. I know an acid catalyst and heat and an alcohol, okay, I'm headed towards the dehydration and elimination. Okay. In this situation, right, I form 1-butene as my major product, but I'm in solution with an acid catalyst. I've got H plus that's freely floating around. And we know, like from the acid catalyzed addition of an alcohol or acid catalyzed addition of water from way back in chapter 6, that this is a nucleophile, that's an electrophile. So that pi density can easily attack that and form a carbocation. Okay. Then I form a secondary carbocation. That's Markovnikov's rule, okay, which is in equilibrium with 2-butene, just picking up the hydrogen again. Right? And this is actually your major product because it's the more stable alkene. Okay. So again, we do our elimination here as we would predict from what we've already covered in chapter 10. Okay. But then the proton from the acidic solution adds to the double bond going right here. Right? That's Markovnikov's rule, forming the carbocation. And then for the elimination reaction, again, Zaitsev tells us to pull the hydrogen off of whichever one had fewest, okay, which is this one. 2 is less than 3, and we form 2-butene. So it's a combination of first Markovnikov and then Zaitsev that gives me that major product there. Okay, again, more substituted chains. So look out for that. Right? Anytime you've got 4 carbons or more, right? Because it wouldn't matter if you had 2 or 3, you'd end up getting the same products in 3D. Right? But once you have 4 carbons, look out for those possible rearrangements. Consider your final product. Can I make it more stable by migrating it over? If yes, then do so. We also have the stereochemistry to consider. Yep. Now, the good news is it's the same stereochem as the E1 reactions that we saw before. Right? This is a secondary alcohol, so it's going by an E1 mechanism. We did the dehydrohalogenations in Orgo-1, so we've got the same stereochem consideration there. Right? We want the larger groups on opposite sides of the double bond. Therefore, trans dominates. Okay? Or E, right? If you don't have the hydrogens, E would predominate over Z. Okay? But these are some harsh conditions, and carbocation rearrangements can hurt your yield overall, thinking about them for synthesis. Okay? Now, under different conditions, you can actually take your E1 reaction and convert it to an E2 reaction. Okay? And look at these conditions, right? We don't have a strong acid catalyst. We don't have heat, right? Because think about that just from an obvious point of view. Heating up acid is something you'd like to avoid if you can. Right? Well, look at this. Now I've got milder conditions and no carbocation rearrangement to do a dehydration reaction. Okay? And this is done now, not by using an acid and heat, right? No sulfuric acid here, but rather using phosphorus oxychloride. Okay, POCl3 is your catalyst here, plus pyridine, and it's actually at cooler temperature, right? You run this a little bit cooler than room temperature. That takes your alcohol, dehydrates it to an alkene. Okay. So obviously it must be doing something with that leaving group. Let's take a look at the mechanism. Your alcohol, right, the lone pair there acts as a nucleophile. It comes in here, does an SN2 reaction on phosphorus to kick off one of the chlorines. Okay. This should look familiar from the first video from chapter 10. Pyridine comes in here and picks up a hydrogen to prevent it from going back. Right. Then pyridine comes in again, pulls off your beta hydrogen. You have a better leaving group here. Okay. And then you get your final product as the alkene. Okay. Easier, more mild way to do these reactions. My focus is less on knowing the mechanism, okay, for my class, because right, it's the same thing we saw in the previous video. You know the general mechanism, how pyridine helps you with these leaving group conversions, right, but know the different ways that you can convert an alcohol to an alkene. Acid and heat is one, phosphorus oxychloride and pyridine is another, and you can also do them with sulfonate esters. Right? Here's that same tosyl chloride we've seen before. Take your alcohol, convert it to a sulfonate ester, okay? Then you just add a strong base, and that carries out an E2 reaction. Okay? So you can do that with a secondary or a tertiary alcohol. You cannot do it with primary because then this would act as a nucleophile instead. Okay? So sulfonate ester, tosyl chloride, and pyridine, that's one way to do it. Okay? Plus then a strong base, or phosphorus oxychloride and pyridine, or your acid catalyzed in heat. 3 ways to do dehydrations. You should also know if they are going by E1 or E2 mechanisms for your alcohols. Okay. So that is elimination reactions. Next, we have oxidation of alcohols for a couple slides here, half dozen or so. First, we're going to think about secondary alcohols, then look at the other possibilities. Okay? Now, secondary alcohols get oxidized to ketones, and we're going to look at a variety of ways to do them, starting with chromic acid. Okay? And we see that oxidation here. It's, again, we've talked about this before. It's an oxidation reaction because we're increasing the number of carbon-oxygen bonds. Okay? We went from 1 carbon-oxygen bond to 2 carbon-oxygen bonds. It's an oxidation reaction. Okay? Chromic acid will do that. Okay? You lose your 2 hydrogens, you form, right, that C double bond O, and you're in business. Okay? You've gone from an alcohol to a ketone. So you'll want to start a list of things that can do it. Chromic acid is one. That's a pretty violent thing to use in the lab. So here's a more gentle way to do it if you're designing a synthesis. These are two things that are coming together, sodium chromate and sulfuric acid. They just form chromic acid in solution. Okay? So you're seeing either one of these, chromic acid or sodium chromate plus sulfuric acid, you know right away, piece of cake, that's going to take an alcohol to a ketone, specifically a secondary alcohol. Okay? Now, primary alcohols don't have an alkyl group on each side, right? So if it's a primary alcohol, you form an aldehyde. And if you're using chromic acid, it actually can't stop at the aldehyde. You can think about the aldehyde as being an intermediate, okay? But chromic acid actually takes an alcohol, a primary alcohol, first to an aldehyde, and then all the way to a carboxylic acid. Jumping back here, if it's a secondary alcohol, chromic acid just stops at a ketone. If it's primary alcohol, chromic acid takes you all the way to a carboxylic acid. If you're designing a synthesis and you want to stop at the aldehyde specifically, okay, primary alcohol to an aldehyde, you use PCC, okay? You just have to know that initial, okay? It stands for pyridinium chlorochromate. That stops it at the aldehyde, and you have to do it in an anhydrous solvent. So you couldn't do this in water because that would end up taking you to a carboxylic acid. You have to have an anhydrous solvent. So this is dichloromethane. We've seen that previously. Here it is again, right? So PCC, dichloromethane, right? So you can write CH2Cl2 or DCM for dichloromethane. And that will take you from a primary alcohol to an aldehyde. What about a tertiary alcohol? That we can't do. Okay, if we have a tertiary alcohol, we can't form another bond to oxygen because we already have 3 alkyl groups coming off, right? That would result in 5 bonds on my carbon there, right? I can't form another CO bond here with having 3 other alkyl groups. You have to have a hydrogen there that you can remove to oxidize, right? Notice in this situation, I'm removing a hydrogen here. I'm removing a hydrogen there. Okay. So if you have a tertiary alcohol, it doesn't matter what you throw at it, that's because it's not going to oxidize. A couple other alternatives to oxidation, right? None of the ones we've covered so far are particularly environmentally friendly. So one other situation to use, right? If you have a primary or a secondary alcohol, is using sodium hypochlorite here plus acetic acid. Okay. These are actually things you've got around the house, right? Sodium hypochlorite, that's typically in bleach. Acetic acid, vinegar, run it at a cool temperature. If you had a secondary alcohol, you're going to a ketone. If you have a primary alcohol, you're going to an aldehyde. Okay. Now we have to use the 2 of them together. In solution, it's actually generating hypochlorous acid, which is HOCl, but that's unstable. So we generate it in solution, and that's a nice, easy, gentle things to use. Secondary goes to ketone. Primary goes to aldehyde. Tertiary doesn't react. Here's what the mechanism looks like. Again, same general scheme that we're used to, right? Activate the leaving group. Okay. Then here we get replaced in an SN2 reaction. Then I have got my base in solution. You can think about it as acetate here or water coming in, plucking off that hydrogen. That electron density from the previous bond to hydrogen goes, it forms a pi bond to oxygen, and you've generated your ketone. If it was primary, you do the same thing to make an aldehyde. So that is the 3rd way to oxidize alcohols. Here's the 4th and the last way from chapter 10. It's called the Swern oxidation, and this is one you're going to want to star, right? Remember, if something has a name, it's typically pretty important. Yep. The Swern oxidation takes you from, if it's a primary alcohol, to an aldehyde, if it's a secondary alcohol, to a ketone, like all these other ones, right? Except for chromic acid, which would take your primary alcohol to a carboxylic acid. So what are we using here? Okay, dimethyl sulfoxide right here. So you can write out the whole formula, or you can write DMSO, dimethyl sulfoxide. Okay. Oxalyl chloride, so C2O2Cl2. And it's got to be run at a cold temperature, -60 here. It's a two-step reaction. That's step one. Step two, right, you add triethylamine. So what's it look like for this gentle oxidation? Consider the mechanism. Okay. Well, the reason that I use DMSO, right, and my oxalochloride here together, right, is that in solution, you put those two together and it generates this dimethylchlorosulfonium ion, generates it in solution, which is used to activate your alcohol. Okay. Gives you a much better leaving group. First, it's an SN2 to kick off chlorine, just like we saw with PCC. If chlorine comes in, plucks off that hydrogen to prevent you from going back. Then you've got a really good leaving group, okay, off of your oxygen. So then you've got a base triethylamine in step two to come in there, pluck off that hydrogen, and then bam, piece of cake, your electron density shifts over, you form your aldehyde. If it was a primary alcohol, your ketone if it was secondary. Okay. Focus number one on knowing all the different ways, all the different combinations of reagents you can use to oxidize an alcohol. Yes. Definitely know what they form. Primary forms an aldehyde, secondary forms ketone, tertiary doesn't form anything, and with one exception. If you use chromic acid, it's going to take your primary all the way to a carboxylic acid. And then last, focus on knowing the mechanisms. That finishes up alcohols. For the remaining two videos in chapter 10, we're going to look at all the other leaving groups that are in the title.